Welcome to lecture 30. So I am starting with the last classes material. So that is the corresponding rule of hypothesis testing. So this particular ratio is called the likelihood ratio. This is called the likelihood ratio because these density functions are called the likelihood density functions, and this is called the threshold. So now I want to show you one thing, like these cost functions are your choice. So for example, let us assume that C10 is equal to C01 is equal to 1 or 10, I don't care, and say C00 is equal to C11 is equal to say 1 or something or 0, such that this thing cancels out. So your C10 minus C11, I am taking uniformly, like I am not saying that this error, type 1 error, is more severe than type 2 error. I am saying that both are similar kind of error and these are similar kind of good stuff. So I can put 0 also. Anyway, so the idea is that this ratio is becoming 1, such that my likelihood ratio threshold becomes just simply PH1 divided by PH0, which I have written as P1 by P0 in the earlier slide. So I can write this as P1 by P0. These are the probabilities of the corresponding hypothesis. Now let us write like plug in just this, putting the cost functions to be the ratio of cost functions to be unity. Then the thing will look like this. So if R given H0, and I am multiplying P H0 with this, divided by f of R given H1, I am multiplying Ph1 with this, then my hypothesis testing becomes like this, isn't it? So I am multiplying this with this and this with this, so it becomes simply this, or I can take this that side as well. Now what are these? So if you know Bayes theorem, so I am bringing Bayes theorem now. Bayes theorem says that you remember that in the last class I told that this like detection is called the Bayesian approach. So why Bayesian approach? This thing will be obvious now. So Bayes theorem says that if you have some observation, that observation is R, and if you have some decision to make, so decisions are basically this H0 and H1, then you have to choose between the two posterior probabilities. So here the posterior probabilities are basically like given R, you have to choose between these probabilities, PH given R and H0 given R and PH1 given R. So I will show that the approach I have taken, that is indeed the Bayes theorem approach, and indeed you are basically maximizing the like posterior probability. So these are called the a posteriori probability or posterior probability. So these are probability, these are mass function. You can see like there are two events and sum of them is equal to 1. So this plus this is equal to 1. Now what Bayes theorem says? Bayes theorem says that you can compute the posterior probability from the prior probability and the likelihood function, likelihood density function. So I am writing the Bayes theorem here. Okay. So Bayes theorem says that you can compute PH0 given R as like f R given H0 into PH0 divided by fr. Now I am writing f here, f density function, because R is a continuous random variable. If R is also a discrete random variable, then it will be simply P. But since in our communication setup these are discrete events, these are discrete like source symbols, you can say, and the output, like the detector input what you are receiving at the end of the noisy channel, you are getting basically a continuous random variable. That's why you are getting the density function over there. This is the likelihood density function, this is the density function of f of R. Now you can compute FR also from these values. So FR can be computed as, so R can happen from two different hypotheses. So either H0 happened or H1 happened. So I can write them as FR given H0 into PH0 plus FR given H1 into PH1. So you can see that if you know the prior probabilities, what are the prior probabilities? So prior probabilities are a priori probability. A priori probability are basically these probability of H0 and probability of H1. These are the a priori probability, and likelihood ratio is the remaining this density function. So you can see from the a priori probability and likelihood you can compute the marginal density function of R, and by knowing them you can compute the a posteriori probability. Now you can clearly see that the numerator here is just this. So what I can do, I can basically take this side, or I can put here only for the numerator and denominator. I'll just divide them by the marginal density function FR. Then what you will get? You will get the posterior probability. So I am dividing both the numerator and denominator by the density function of marginal density function of R. So I am getting probability of H0 into F of R given H0 divided by F of R divided by probability of H1 into F of R given H1 divided by FR. So this is what you are doing, and here it is H0, here it is H1. So Bayes theorem says that ratio is basically the posterior probability. So what you are getting is basically probability of H0 given R divided by probability of H1 given R, and you are choosing whether it is greater than 1 or not. So I can write in this way. I can just take that side, and I can write that probability of H0 given R is greater than equal to probability of H1 given R, and if this is greater than, I will choose H0. If that is greater than, I will choose H1. So essentially what you are doing, you are computing the posterior probability of a particular hypothesis based on the evidence or observation, and whatever is maximum, you are choosing that hypothesis. So this kind of detection problem, the approach is called the MAP approach, or maximum a posteriori approach. So this is called the MAP approach. Full form is maximum a posteriori approach. Probability. So what it says that choose that HI which basically maximize. So I can write I, basically I is the argument. I is equal to argument max of P H I given R. So based on the evidence of R, I is equal to here 1 and 2. Okay, so this is what maximum a posterior detection is. So you are basically maximizing the posterior probability, and that we are not defining, we are actually deriving. We derived it from our earlier analysis that if you choose these as symmetric, then such that this ratio becomes 1, then your actual detection, what you have done, that optimal detection, that becomes MAP detection. Okay, so this is called MAP. However, for communication applications, in communication in DGCOM, we know that if source coding has been done, then like source coding implies equiprobable sources, equiprobable symbols. That implies that P of H0 is equal to H1 is equal to half. So that enforces that simply that will also cancel out, that will also cancel out. So you will get the likelihood ratio as your decision rule. So your likelihood ratio, which is basically f of r given H0 and f of r given H1, and you are choosing based on that This is your decision rule. So this decision rule, which I can write as f of r given h0 greater than equal to less than f of r given h1, this is h0 and this is h1. This particular rule, where you are comparing only the likelihood density functions and you are choosing the corresponding hypothesis based on whichever likelihood density function is more, this is called the maximum likelihood detection or ML detection. So these are the two paradigms you can say in detection theory, where one is based on the Bayesian approach, where you compute the maximum a posteriori and you work on that. Another is like in the communication setup or in the radar setup, or you don't know anything about the prior, you have no idea, like biomedical setup, so you do not have any idea about the prior. Then what you can do, that it is a natural process, you can assume that that is maximum entropy, and maximum entropy for a finite like discrete random variable, it is equiprobable. So then maximum likelihood is the setup. Okay. But there are cases like machine learning theory, where maximum a posteriori also works if you have like different source probabilities. It can work in communication also if you did not do the source coding. Then it is very well possible that different symbols have different probabilities. That you have seen in Huffman encoding, right? Originally the source symbols can be different. So these are the two major paradigms which we will take. And you can see that they are very closely related. So only difference is basically this prior probability. Okay. So what I'll do, I'll basically move towards one example first, that how does the decision boundary, and I'm starting with the simplest one, that is the binary PM, or like the example we have shown in the last class. So let us show that how will be the regions. So example 1, let us take the binary PM or antipodal PM. There are different names, or it can be said BPSK also, like binary phase shift keying, the same thing. So our observation, like the sets are essentially these. So this is say A0. I am writing A0 is equal to say +1, and this is say A1, which is say -1. So 0, like symbol 0 is mapped to +1, symbol 1 is mapped to -1, and they are having the probabilities. This is say P0 and this is say P1. Okay, and we know that the random variable which is added is a identified Gaussian noise random variable with a variance of n0/2. So I am just not deriving everything again, I am just applying the MAP formula. So MAP formula says, so what will be the likelihood ratio? So if I compute the likelihood ratio, it will be f of r given h1, h0, so this is h0 and this is your h1, divided by f of r given h1. And what are them? This we have computed in the last class also. So that one was here. So here we have already seen it. So it will be 1 by root over of pi n0 e to the power minus r h0 is here, so r minus 1 square by n0 divided by 1 by root over of pi n0 e to the power minus r plus 1 by n0. So these constants cancel out. The remaining thing is e to the power r plus 1 square minus r minus 1 square by n0, and this I can compute as 4r, e to the power 4r by n0. So that is the likelihood ratio. And what is the threshold? Threshold is simply p1 by p0. P1 by p0. So p1 is basically this one, yeah. So p1 by p0. So my decision rule is MAP is likelihood ratio is greater than less than threshold. This is h0 and this is h1. So I can write e to the power 4r by n0 greater than equal to p1 by p0. This is h0, this is h1. So I can take the logarithm this side. So actually in many applications where your likelihood function is Gaussian kind of, so you can always take logarithm, and that logarithm is called the log likelihood. So log likelihood ratio, and it is called LLR. So that is equal to basically ln this, which is equal to 4r by n0. So if you take logarithm here, you will get basically 4r by n0, that is greater than equal less than, this is h0, this is h1, log p1 by p0. So clearly you can get the relationship for r. So if r is this, n0 by 4 log p1 by p0. So this is the threshold value. This I can write as r threshold. And if r is greater than r threshold, you choose the hypothesis h0. If r is less than r threshold, you choose the hypothesis h1. So our easiest case is for communication application where p1 is equal to p0 is equal to half. Clearly this will be 1, log 1 is 0. So clearly this is 0. Your r threshold is 0. So for equiprobable, p1 is equal to p0 is equal to half, your threshold is 0. So then your detection rule is MAP gives r greater than less than 0. This is for h0 and this is for h1. So that is what you are obtaining for this binary PAM modulation. This is obvious because you are putting that both of them are having equiprobability, and there are this Gaussian kernel which is adding as the noise. Then the threshold has to be the midpoint. So this is the midpoint, which is the threshold, and anything above is your h0, anything below is your h1. Okay. Now let me talk about the probability of error, which I discussed in the last class a little bit, but let us now get some some functional form of the probability of error. Of course this detection will not be error free. So what will be the probability of error? So this one is +1, this is -1. So what is your f r given h0? So that is basically this kernel, this Gaussian, and your f r given h1 is Gaussian here, and this is your 0 point. So we know that if this is your threshold, this is your r threshold, then anything if originally it was h0, which is -1, this is your h1, which is -1, and by the random variable you are getting the r value greater than 0, then that is error. So that is your type 2 error. So type 1 error is basically h0 is correct and you have choosing h1. So that is possible when h0 is true, and that is happening with probability half. So p0 is equal to half, but your r is less than 0. So what is the probability that r will be less than 0? So probability of error when r is less than 0, that is under h0. So that is equal to probability of r is less than 0 under h0. What is that probability? So that probability is basically the integral over the entire region of h1, that is -infinity to 0, of f of r given h0 dr. This probability, isn't it? So if you know about Gaussian kernels, so you can clearly see that you know about Q function, right? So Q function says that Qx is basically this probability x to infinity, the standard normal, 1 by root 2 pi e to the power minus x square by 2 dx. This is called Qx. Okay. So using Qx you can compute the error probability. So what I will write, I can write the structure here. So minus infinity to 0, 1 by root over of pi n0 e to the power minus r minus 1 square by n0 dr. This integral is the probability of error. Okay. It is your exercise homework. Write using Q function. So what will be the argument of the Q function? I could have written, I am not writing. So this is the probability of error when original thing is H0. Similarly for type 2, H1 is true or was true. It has happened already. Your P1 is half. So now your detection is R is greater than 0, like your observation is, then your probability of error, like error has happened with H1 is essentially probability of R greater than 0 with H1, which is essentially 0 to infinity f of R given H1 dr. So again I can compute the integral minus 0 to infinity 1 by pi n0 to the power minus r plus 1 square by n0 dr. So we got two probabilities. So now I can ask you that what is the expected probability of error. So expected of PE, probability of error, I can say. Probability of error is essentially P0 PE given H0 plus P1 into PE given H1. That is your total probability of error. So you have already all the values. These are half. So you compute these in terms of the Q function. You will get something. Compute that in terms of the Q function. And Q function, there is standard table for Q function. If you give the argument, you can compute the value, or vice versa. Like if you give the error value, it will say that what is the argument of the Q function. So people have already developed the tables for that. So this is the probability of error for the bipodal this PM, this kind of application. Now let me move towards from this very simple detection to a little complex, little complicated detection problem. So which is basically the M-array detection problem. I am talking about the M-array first. Then I can move towards other applications. For example, vector channel. Till now, what we are doing is only scalar channel. So if you are having a vectorial environment where R is a n vector, your noise is also n vector, your symbols are also n vector, then what will be the form? We will discuss that. But before going there, I am just stating the M array. It will not take much time. The argument, analysis, everything will be similar. So I am not going to discuss the entire detection methodology using some cost function and all, because we know that there are two detection schemes, either MAP or ML. So I can write only ML also, because this is communication anyway. Okay. So nevertheless, let us write down. So M-array detection, and I am writing only maximum likelihood for ML. Okay. So M-array means there are M symbols in the alphabet. So your alphabet is having M symbols. Say A0 to AM. Okay. So how many hypotheses? Of course, you have hypothesis number is M. So you have total M hypothesis. Okay. The probabilities I am assuming to be all of them ak, which is basically probability of hk, I can say, is 1 by m, equal probable. Okay. Then my ML rule says that the at the detector, so what is happening, you are having some signal x which is coming from this alphabet. So this is the constellation alphabet. One of the signal is coming, this is the like that particular scalar, and you are adding the random variable n. Still now this is scalar, this is MAP, okay, but there are m number of symbols. This is the Gaussian noise and you are detecting R. Now your job is that based on the R you have to choose which hypothesis. So maximum a posteriori, if you approach that, you have to basically compute the maximum of the posterior probability. I am going for only the maximum likelihood. Then your m dash, because this R from here, this is your detector, you have to detect some am dash, isn't it? am dash, I can say. So which will be one of the like member of the constellation, and I am expecting that this value is exactly same as the value of the like source symbol which has been transmitted. So this m hat, basically the argument is basically the argument of the maximization problem of the likelihood function, likelihood or log likelihood. So likelihood function, which is f r given hk, and you are running for all k is equal to 1 to m. So you compute basically all the maximum likelihood expression, like likelihood expression, you compute the maximum, and for which k you are getting the maximum, that is basically the argument of the detection. Okay, so this is all about M-array detection. Now I am moving towards the vectorial scenario, because that vectorial scenario will give us some more clue, because we can derive like forward, and we can show you that how we can implement a circuit by which you can compute this thing. Okay, so for that let me start. How do I let me think, how do I proceed for the vector channel? Okay, so for the real vector channel, let me do it first. And in the generic A-Barry scheme. Okay, so what I'm doing, so right now it is, assume it is n dimensional. So n dimensional can be visualized in different ways. N dimensional can be visualized that you are taking n symbols from a PAM like modulation scheme, or you can take n by 2 symbols from a QAM modulation scheme, etc. However, the signal is n dimensional. So if it is PM, suppose this is the timeline, what you are doing, you are basically choosing the symbols like this, x1, x2 up to say xn. These symbols you are choosing, and for every symbol you are adding one noise. So the noise dimension is also n. There are n random variables, and they are all IID, independent identically distributed random variables. We know their statistics as well. So what is the joint statistics of n of such noises? I am writing n. I should not write, because noise I am writing as n. So I should write something else. I should write capital N. That will be better. So capital N dimensional, suppose. So your noise vector, which will look like now n dimensional, will look like some n1 up to nn, and this vector, the density function will be, so f of n will look like 1 by pi n0 to the power n by 2 e to the power minus the second norm of noise, second norm square, divided by n0. This is basically sum of square of all the terms, isn't it? So this is what the noise is. Now I will apply our maximum a posteriori or maximum likelihood problem. So I'm working only on ML right now, but MAP is similar. Only you have to multiply with the prior probability. So what will be my in this setup when it is vector? So vector means your this vector is coming. This is say n, and your addition is the noise, which is also you are adding n, 1 to n say, and you are receiving the r, which is also n dimensional, and now you are performing detection. What you want to get? You want to get the so what is the dimensionality of this? Let me say, because ultimately what you will get one index. What index it is? So how many different possible x vectors are there of n dimensional vector? So every element can be of one of the m possible symbols. So there are total the cardinality of this set. So if I write this vector belongs to this set, this cardinality is basically m to the power n. So one of the m to the power n symbols symbol vectors is coming, and you have to choose the index which is one of those. So my m dash is basically one of those m to the power n vectors. Okay, then I am choosing that m dash, that m hat. Yeah. So my m hat is argmax, and when your m is between 1 and m to the power n. Okay, your f of r means the vector, so I should write the vector given the symbol which has been coming. So all the possible symbols, so I can write h m, this is m, and how many hypotheses? Of course there are capital M to the power m hypotheses. So you have the total set of hypotheses which is starting from h1 to h m to the power n. So this is the total set of hypotheses. So if it is say m is equal to 4, n is equal to 10, so 4 to the power 10, like that. Now what is this likelihood? So the likelihood depends on this hm. Hm is basically the hypothesis, so it depends on a particular vector, and that vector is one of these vectors. So one of these vectors, so element of that. So I can write it as am or something like that. So I can write it as am 1 m to the power n f r given say am. This am is basically am belongs to a to the power n. Okay, then this expression I know, because r is what? R is basically am plus noise. Am plus noise, the n-dimensional vector given am for all m. I know that this is same as this. Now what is this? This is basically the mean is am. So I can write now the straight away the Gaussian form. That Gaussian form is 1 by pi n0 whole to the power n by 2 e to the power minus, the noise is essentially the symbol, like the n is equal to r minus am, I can say. So r minus am square by n0. This is what it is, isn't it? Now what I can do, I can apply logarithm over there, because logarithm is monotonous function, so it does not change the argmax. So apply logarithm now. So argmax for all m log of 1 by pi n0 to the power n by 2. I can take n by 2 outside. This is a constant, minus r minus m square by n0. So this is a constant, it goes out of the argmax, because it appears with all the terms for all m, isn't it? So now there is a minus sign, so I can change from argmax to argmin if I want to get rid of that minus sign. So I am straight away writing argmin for all m r minus m square by n0. n0 is also a constant, I can get rid of that. So it is a positive constant, so I can get rid of that. So this is equal to argmin of r minus m square. I can get rid of that square also, because square is also a monotonic function, monotonically increasing function, so it does not change anything. So essentially the entire problem of detection, maximum likelihood detection, is nothing but minimizing the Euclidean distance, Hilbert space distance between the received signal and the symbols. So those symbols are one of those vectors. So total there are m to the power n vectors. You find out that your received signal is closest in terms of the L2 distance. This is L2 distance among all the possible symbols, and whichever is minimum, take that. So that isn't that obvious? This is like minimum nearest neighbor classifier, I can say. So in like learning theory literature, pattern recognition literature, it is called the nearest neighbor classifier. So you find out, like from the R, you find out that whichever vector is closest to that received R, and choose that. It does not stop there. What I can do more is I can expand this square. So m hat is equal to argmin, this r minus m square. This is for all m. Now I can expand this quadratic form. So what I will get, argmin of r square plus m square minus 2 into rm, the inner product. Now this inner product, this r and m, they can be complex, then I have to take the real of this. Okay, now out of this, r does not change with m, so you can get rid of r also. So you will get essentially this m square minus, or m square by 2 minus r am. I can convert it to argmax again. So r am minus m square by 2. Now what is m square by 2? M square by 2 is basically energy of that signal. Now if you have some like scheme, say not PM scheme, it can be PM scheme also. Suppose bipodal PM scheme, whatever we have taken. So suppose if your modulation scheme is bipodal PM, then your m is equal to 2. Now you take some n is equal to something, n can be 100 or something like that. Now interesting thing is that all the AMs will have same energy, because this is bipodal, so this is +1 and -1. So if you look at the different vectors, I'm talking about say 10, n is equal to 10. So how many vectors are there? So 2 to the power 10. So 2 to the power 10 possible vectors. Let me write even smaller such that I can enumerate. So let us take n is equal to 4. So total m to the power n is equal to 2 to the power 4. So that is 16. So what are the different possible vectors? So what are those AMs? So AMs, the set of m, which is basically the alphabet to the power n, that set is basically this. Say -1, -1, -1, -1, -1, -1, -1, -1, +1. This is just binary encoding, isn't it? Up to +1, +1, +1, +1. Now if you look at them, so that is your AM. So if I ask you what is AM square, so this is a vector. The vector elements are this. So the L2 norm square is summation, their amplitude square, individual amplitude square. So AM k square, k is equal to 1 to n, which is 4 here. So that value is 4 for all m is equal to 1 to m to the power n, which is 16. So for everything the value is same, identical. So if you take this simple like modulation scheme, this value is also constant. Okay, then what result that is given? There are like this equi-energy thing is also meaningful, because you don't want your communication system to like fluctuate in terms of its energy. That's why you either take this kind of simple this bipodal, if the requirement of data transmission is not that high, or you can take a QAM which is on a circle. So basically phase shift keying, PSK kind of structure. So where your constellation is basically on a circle in that two-dimensional space of QAM. Then also every symbol is having identical energy. So if you take a vector of size n, all the vectors are having identical energy. Okay. However, general QAM will not have that, like the rectangular grid or like hexagonal grid, some other kind of grid. It may not have different energies. But if the energy is same, then this ML will become simply, if all AM square are same, then the ML scheme, ML detection becomes argmax for all m simply the inner product between the vector r, n-dimensional vector r, and the n-dimensional vector am. Okay, so inner product is what? Projection. Basically you are projecting. So you have one r, you have like one r, you have m to the power n m's. So they are the vectors. Suppose in some capital n dimensional vector space, they are the vectors. Okay, you have one r. Now you project it and see that where you are getting the maximum projection, where the inner product is maximum. So if the projection is maximum, that means you are closest to that. So you can compute from there. Now how to using a circuit, how can you compute? You can measure r, you can get r, the vector, and then in the digital domain you can compute it, because am is also available in terms of the vectors, like I have written it out. So you can compute that, you can like have that in a circuit, but there is a trick. We can compute this using matched filter as well. So I'll talk about that later. But before going there, let me go somewhere else We will talk about the circuit once we complete that. No? Let us proceed then. Let us go back to the earlier form, that is the minimum distance between the received vector and the possible symbol vectors. So observe m hat is equal to arg mean of r minus m square. So where m is between, and you again I am reiterating to tell you that this is basically the vector of length n, and so what I can write, this is the 2 norm, L2 norm. So I can write in terms of its the elements. So the elements are, r is a vector of length capital N, where the elements are say r0 up to r1 to rn say. It can be shifted, okay, it can be shifted to any arbitrary number, that does not like change anything. This is a vector of size n. So like I have already drawn that in the earlier. It is basically these time points, isn't it? Similarly, this is the source, but after adding the noise you receive this vector. Now am is one of those vectors, like here you have seen 16 vectors. So one of those vectors, so that am will also look like this. It will have a form like this. So am1 up to am say n. Okay, so I can write it as summation r k minus am k square, k is equal to 1 to n. I can write like this. That's the 2 norm. So the expansion is like that. Now things are becoming interesting, because this is basically the time instance, k is equal to 1 to n. Now you observe that like this is your time point, and this is your 1, this is your 2, up to this is your n. This is some arbitrary k, and this is the space of say real space of PAM. Okay, so in this space you have different symbols. So one of those capital M symbols, let us write them to be B, that will be better. So where did I start? Yeah, the symbols are say, these are not A, these are say B, that will be better. B0 to say BM. Okay, those are the original symbol for one time point. So your AM, what we have developed after that, AM is nothing but a vector of those B's. So one example of AM is say B0, B1, B4, B7, BM, etc. etc. So this is a vector of n cross 1. Those are the points. So in this diagram, what I am developing now, here, so the corresponding B points are say these are the B points, B1, B2. So this is the PAM direction, say BM. These are the points. So same points. So my argument is that since I want to minimize this entire term, and everything is square, square means positive. So to minimize this entire thing, the sum, you have to minimize every term for every k. Is that argument valid? So for every k, starting from k is equal to 0 to k is equal to n, the r should be nearest to the chosen one. So whatever be the m hat, so at that particular k, that corresponding am hat k should be closest to the received rk. So suppose here the rk is so the rk looks like this. Suppose rk is continuous, right? So rk is like some any value it can assume. it can assume value like say here, something like this. So what I'm saying that for every k, find out the corresponding b which is closest, and that will be your the corresponding vector value. So this is basically a vector for of b's n cross 1. These are the different b values. So how will you fill up this thing? For m hat say, so you will fill up that at the first instance find out that which b is closest to r0 r1. So this is your r1. So if it is b2, fill up b2. Find out which one is closest to your r2. If it is b7, fill up b7, like that. So essentially the vector detection is nothing but scalar detection. So at every instance of time you find out that which point is nearest to you, choose that. That's it. So this gives us a really nice revelation that we really do not have to do vector detection, since at every instance I can perform individual detection like scalar detection, be it in like PM or QM, whatever. So that is good enough. What is the condition? Condition is definitely like every source symbols are independent, equiprobable, and the noise is, of course, you have the KL expansion and all. So this particular observation gives us a really nice point of view. So with this I am concluding this detector design thing. In the book, if you go, that there are lots of different issues, mostly they are historical, and actually I did not discuss any other modulation as well. So there are lots of historical modulations which are present. I did not discuss. It is okay, like to have only the understanding of QAM. That is the most fundamental. Similarly, the baseband to passband modulation, I discussed only the regular like DSB, double sideband quadrature carrier. That is the only one I discussed. In reality, it can be any of those frequency modulation, phase modulation, etc. So I really don't want to go into those analog communication concepts yet again, since we are running out of time. We have many things to cover. So with this I am concluding this. Regarding the circuit diagram, so circuit diagram is basically, you can write in terms of the inner product if your energies are same. If the energies are not same, then you have to have the bias term. This is like a bias term. So this inner product you can compute in the vectorial scenario, but then you understand that that vectorial thing is not required, because you can perform it at every instance of time. That one shot detection, that is good enough. So that you can perform easily. So just by computing observing R is basically the matched filter output when you are sampling at the right time. Then find out just by simple thresholding operation that it is close to what, and thresholding you have seen already in quantization. So it is like that. So you see that where it is. So I can show you that how the circuit will be. Circuit is basically like for the scalar one. So your signal is coming RT, you are having your YT that is passing through the matched filter, and then you are sampling it. So if you sample it, you are getting basically R. That R, what you have to do, you have to basically threshold it. So you have all the different B's available, right? The layers, the corresponding values. So you find out that it belongs to which class. So suppose these are starting from say some B1, B2 up to say B capital M, and you see that R falls in which group. So whichever be the group, the corresponding representative points, that will be your output, that will be your detection. Okay, so this is simple thresholding operation. Okay, after this I am going to start the bounds of probability of errors. this is something which is interesting, like it is having some historical relevance also. I'll talk about upper and lower bounds. I want to show basically that the probability of error depends only the nearest neighbors, the distance between the nearest neighbors in the constellation. That is what I want to show you. So let me go to those bound issues. Oh, we are already running out of time, so 1 hour is almost over. So I'm not actually starting the bounds today. Let me make another video. It will be a little smaller video, half an hour video tomorrow, talking about the different bounds. Okay, so till then, bye.